let's get started with today's lecture, which is on Chapter 7, which is acid-base chemistry and pH. So we have a fun set of experiments. In terms of labs, we're going to be doing the lab for this experiment next week on account of the Thanksgiving break. But we're going to be lecturing today on Chapter 7, acid-base chemistry, and we'll be continuing on and continuing to work on the previously assigned laboratories. Okay, so let's talk a little bit about acids and bases, and let's define acids and bases. There are two major ways of defining acids and bases. The first is the Arrhenius definition. An Arrhenius acid, quite simply, dissociates to give H plus and their conjugate base A minus in solution. So the key thing I want you to remember, if you're dealing with an acid, they make H plus. Okay? And more specifically, they dissociate to make H plus. Now, a classic example of this is hydrochloric acid. So as we can see, hydrochloric acid can dissociate. So if you think about a hydrochloric acid, we can break the hydrogen chlorine bond and we can make, in turn, H plus and Cl minus. Okay, this is a bond breaking event. We're dissociating this bond to make H plus and Cl minus. And we call this anionic species that has lost a proton, a single proton, the conjugate base. Does that make sense to everyone? So the conjugate base of an acid has lost a single proton. It differs from the acid by a single proton. Okay, so the corollary to the Arrhenius acid, which makes H plus, is the Arrhenius base. And an Arrhenius base reacts with water or dissociates to give OH minus, which is known as hydroxide in solution. So anytime you see hydroxide, I want you to think a base. So a base can be thought of simplistically as a species that generates hydroxide in solution. Does this make sense to everyone so far? So a classic example of this is a metal hydroxide like sodium hydroxide, which dissociates in solution to yield hydroxide and sodium plus. Now, another example of a base would be an anion such as methoxide. In this case, it reacts with water, and in turn, we generate hydroxide. So these are the two major types of bases you will see: soluble hydroxide salts and species that react with water to make hydroxide. Is everyone comfortable with this so far? Okay, so let's keep going now, and let's talk a little bit about the Bronsted definitions. So a Bronsted acid can be thought of as an H plus donor. So for example, if we mix hydrochloric acid with water, hydrochloric acid will donate H plus to water to make H3O plus and Cl minus, which is the conjugate base. Does that make sense to everyone? Does everyone see how hydrochloric acid is donating, giving, losing a proton? And so it would be called a Bronsted acid. So in this case, H3O plus has gained a proton. We call H3O plus, quote unquote, hydronium ion. It's a super common ion in water when you're dealing with acid-base chemistry. Now, the corollary to a Bronsted acid is a Bronsted base, which is an H plus acceptor. Now, an example of a Bronsted base would be ammonia. Ammonia, in this case, is accepting H plus, and the way you can really help and notice potential Bronsted bases is if you draw out their Lewis structure, you notice what's so special about ammonia? What does ammonia have? What do we call that pair of dots that I've drawn? A lone pair, yep. So lone pairs are a pretty strong indication that you're likely dealing with a basic species. Not always, but it's a pretty good rule of thumb, especially if it's on nitrogen. Okay, so does everyone see how ammonia is functioning as a Bronsted base? Because it's picking up a proton. It's gaining H plus. And as we notice, what do we make? What very important anion do we make when this base reacts with water? Hydroxide, okay? So anytime you see the generation of hydroxide, we're likely dealing with a base. Okay, now in aqueous solution, you don't generally have H plus floating around. Instead, hydrogen ions will react with water to form hydronium ions. So H plus and H3O plus are used interchangeably in water. These can be considered functionally equivalent. That's what these three lines mean, just they're functionally equivalent species. It's more correct for you to write things as H3O plus because that's what's actually in solution. But H3O plus is just representing H plus. Does that make sense to everyone? So in water, H plus converts to H3O plus. Okay, so let's talk about acids and bases in aqueous solutions. So acids and bases are covalent compounds that are typically soluble in water for the most part. There are, of course, many organic acids that are covered in later courses that aren't so water soluble, but most of the acids that you'll see and handle on a day-to-day basis are going to be pretty water soluble. Now, looking at our two definitions of an acid, we can either view it as a proton donor or a species that dissociates to give H plus and their conjugate base. And let's define the conjugate base. The conjugate base is an anion with exactly one less proton than the parent acid. Note exactly one less proton, no more, no less. So in this case, if we label HCl, hydrochloric acid, as our parent acid, what is the conjugate base of HCl? What happens if we lose a proton from HCl? What do we get? What's the conjugate base of HCl? Would someone like to type it out or say it verbally or in the chat? Yep, Cl, and more specifically, Cl minus. Perfect, perfect. Always make sure to mention the charge because as we'll see later on in the chapter, the charge has a pretty dramatic effect on acidity. Okay, the next thing we're going to look at are bases. So bases, we can view them in two major ways. They're either thought of as an H+ acceptor or a species that reacts with water to give hydroxide and the conjugate acid. Okay, and the conjugate acid, let's define the conjugate acid. It's a neutral or cationic species with one more proton than the parent base. So again, the only difference is one proton. So here's a pretty interesting example, and this is part of the reason why this is one of the potential reasons why sodium hydride can potentially light on fire when you place it in water. So would someone like to identify in sodium hydride, what is the basic species? What is our anionic species in sodium hydride? What is the anion in sodium hydride? So sodium has a +1 charge. So I see in the chat. So thinking about sodium hydride, we have sodium plus. And what's our anion? What has a negative charge? What's our anionic species? What is the basic anion in sodium hydride? So if sodium has a plus charge, what has the minus charge? H minus, exactly right. H minus is known as hydride. And when sodium hydride reacts with water, it makes H2, which is hydrogen gas, which can be viewed as our conjugate acid. So this is why you'll often see bubbles, and hydrogen gas is quite reactive and can often catch on fire if it reaches sufficient temperature and oxygen concentrations. Okay, so I like this example because it helps you sort of get in the rhythm of identifying the basic anion and the conjugate acid, where the base is your anionic species that's reacting to make hydroxide, and your conjugate acid is the conjugate base plus one proton. Now, the other more common way that you'll see bases react or behave is that they dissociate to generate hydroxide in solution. This is commonly seen if you have a soluble metal hydroxide, such as sodium hydroxide, which breaks down into its component ions when it dissolves as it enters solution. Do these ideas make sense to everyone so far? Does this make sense to everyone so far? Perfect. So let's talk a little bit about what makes a base a strong base. So your strong bases are soluble ionic salts containing hydroxide. These are typically your group 1A and group 2A hydroxide salts. These strong bases dissociate completely in solution to give hydroxide and mainly ions in solution. So an example of this would be, for example, lithium hydroxide, which breaks down into lithium plus and OH minus. Would anyone like to propose another formula for a group 1A or group 2A hydroxide salt? Would anyone like to perform or provide another formula for a soluble hydroxide salt?
NaOH,
Yep,
then get
yep.
the sodium plus OH.
Yep, sodium hydroxide is a perfectly valid example, and that dissociates in solution to yield sodium plus and OH minus. Calcium hydroxide is sparingly soluble, and it can dissociate to yield calcium 2 plus along with hydroxide. So these are some examples of strong bases. These are soluble hydroxide salts. Another example was potassium hydroxide. That was mentioned in the chat. Wonderful. That's another reasonable proposal. Wonderful. Now, weak bases. So in general, most of the weak bases that you will see in this class and in organic chemistry for that matter are compounds containing an NHX or an amine functional group. So examples of this could be something like ammonia, for example. Now, the main difference between a strong base and a weak base is that weak bases dissociate a really, really small amount in solution. And as a result, we have mainly dissolved molecular compound in solution. So for example, if we think about ammonia reacting with water, we only get a really small amount of forward reaction to make hydroxide and ammonia. The majority of our ammonia molecule. So if we draw a picture, let's do a pictorial comparison. So if we look at a strong base, so if we look at a strong base from a zoomed in perspective, we'd see a lot of ions and a lot of hydroxide present in solution. If we compare that to a weak base, and we look at the same fish tank view, we're going to see mainly molecular ammonia in solution. And we'll see very little hydroxide and ammonium ion. So the main difference between a strong base and a weak base is the degree of dissociation and degree of reaction. Weak bases ionize and dissociate a very small amount in solution. And as a result, we don't have a lot of hydroxide floating around in solution when we have a weak base. Does that idea make sense to everyone? Do these pictures make sense? Perfect, perfect. So let's talk next about a strong acid. So these are the 6 strong acids that you'll have to be familiar with. You have your major halogen acids, hydrobromic, chloric, and hydroiodic acid, sulfuric, perchloric, and nitric acid. These are your textbook strong acids that I want you to be familiar with. Okay. So now the main feature of these strong acids is that they dissociate completely in solution to give H plus and their conjugate base. So we have mainly ions in solution. So for example, nitric acid will break down to yield H plus and NO3 minus. So H plus and the conjugate base. Likewise, sulfuric acid. How many protons can sulfuric acid dissociate?
2H.
Yep, exactly right. So sulfuric acid can dissociate to 2 equivalents of H plus and SO4 2 minus. Okay, so if we look at this from a molecular perspective, so if we look at nitric acid from a molecular perspective, if nitric acid is a strong acid, will we see mainly ions or molecules? What will we see? What should I draw? Mainly ions? Yep, perfect. Exactly right. So we should draw primarily H plus and NO3 minus. Strong acids completely dissociate. Does this make sense to everyone? Perfect. So let's talk about weak acids. These are essentially, to make things easy, any acid not listed as a strong acid in our table, both in the book, and you'll see a table later on in the notes. If it's an acid and it's not in this list of strong acids, you'd be reasonable to assume it would be a weak acid in most cases. The main feature of weak acids is that they dissociate less than 1% in solution. We have mainly dissolved molecular compound, mainly molecules dissolved in solution. So let's look at an example. So acetic acid. Is acetic acid on this above list? Is acetic acid matching any of these? No. Okay, so it's a weak acid. So then we're not really going to see a lot of dissociation. We're primarily going to have molecular acetic acid in solution, and we'll have a little bit of ions, not a lot. So if we're drawing a picture of acetic acid, which is a weak acid, we will have mainly molecules in solution. So in the case of acetic acid, we draw out our acetate and H plus, and we'd have primarily molecular acetic acid. So our drawing should reflect that. Okay, so the main feature of a weak acid, they don't dissociate to a large extent, and they don't dissociate very efficiently. And as a result, we have mainly molecular species in solution. And as we'll see later on, because weak acids don't generate a lot of H plus in solution in most cases, in general, they have a less dramatic effect on pH than a strong acid. And the same is true for weak bases when compared to strong bases. Does this make sense to everyone so far? Okay, so here's a list of common strong acids and common strong bases. This would be good to memorize or be familiar with at least. For the strong bases, if you just remember the 1A, 2A rule that I taught you earlier, that'll get you most of the way there. And the strong acids, you just remember the halogens and your 4 strong polyatomic acids. So to help us reinforce this idea and to help us become familiar with the common strong acids and strong bases, let's take a look now. And let's look at the following list and characterize the following as a strong acid, strong base, weak acid, weak base, or neither. Okay, so let's go through this list together. Let's go through this list together. So the first one is perchloric acid, HClO4. Would we consider this a strong acid, weak acid, strong base, or weak base? What do we think for perchloric acid?
Strong acid.
Yep, exactly right. Okay. Next is lithium hydroxide. So I see this hydroxide. So what does that tell us?
Base.
Yep. And in this case, are we dealing with a strong or weak base?
Strong base.
Yep, it's a group 1A metal hydroxide. So it would be a strong base. And in both cases, because we have a strong acid and a strong base, so for perchloric acid, it will break down into its component ions of H plus and ClO4 minus. Likewise, lithium hydroxide will break down to lithium plus and OH minus. Let's look at this next case, sodium bromide. So are there any features of an acid or base in sodium bromide? Anything that reminds us of an acid or base?
Neither.
Neither, exactly right. It is still soluble, so it will break down to sodium plus and Br minus. Just no H plus or hydroxide floating around in solution. Okay, let's do this next one together before I let everyone break down into groups and tackle the next few. So this formula may look a little odd, but it's important to keep in mind H2C2O4. Does anyone recognize this formula? What common acid is this? We've seen this in the nomenclature chapter. What acid is this? H2C2O4. To give everyone a hint, this is known as oxalic acid. Now, based on the name, we can definitely conclude it's an acid. And would we expect this to be a strong or weak acid?
Weak acid.
Yep, exactly right. So we'd assign this as a weak acid. And as a result, would we have mainly ions or molecules in solution? For a weak acid, do weak acids dissociate very much?
No.
Not really, exactly right. So we'd have mainly molecular oxalic acid in solution. Okay, so with these representative examples in mind, I'd like us to work on 5 through 10. And let's try to come up with some reasonable assignments for whether each of these species are strong acids, strong bases, weak acids, or weak bases. And then we'll discuss these questions in about 4 to 5 minutes. So let's try our best to identify each of these species 5 through 10 as strong acids, weak acids, strong bases or weak bases, and try to describe the major species in solution. and we'll discuss in about 4 to 5 minutes. Let's try to get some proposals and assignments in the chat, and it would be perfect if you could also include a dissociation equation and whether you think you'll see mainly ions or molecules. And try to get as many of them complete as possible during this problem solving period. And then we'll discuss momentarily. And let's try to get some proposals in the chat and we'll discuss momentarily. And if there are any questions or if there are any proposed responses, don't be shy to share them verbally or in the chat. And it's great to see we have a few proposed assignments in the chat. Let's keep working through this example and then we'll discuss in about another 2 to 3 minutes. And ideally, it'd be great to see a range of student responses. So that way I can get a sense of how the class is progressing through the material and provide any feedback on their responses. The responses that we're getting in the chat so far look good. Let's keep working through and we'll discuss in about another minute and a half. And it's great to see that we have responses for each of these structures and formulas. So then, now that we have this information in mind, let's take a look. So H2S. So H2S, in terms of its formal name, the name provides you a pretty invaluable hint in classifying compounds. Is H2S, based on its formal IUPAC name, is it an acid or a base? H2S.
Acid.
Yep, it's known as hydrosulfuric acid. And based on the list of strong acids that we were provided, is hydrosulfuric acid a strong acid or a weak acid? Is
Weak acid.
Yep, exactly right. Hydrosulfuric acid is a weak acid. And as a result, we would have mainly molecules in solution. Perfect. Okay, let's continue on with this trend.
What the
H2CO.
molecules linked at the H2S?
Yep, exactly right. So we'd have primarily H2S floating around in solution and a very small amount of H plus. Does that make sense?
Yes.
Perfect. Likewise, as we'll see in the second example, H2CO3. Would someone like to comment? What is H2CO3? Is it an acid or a base?
Acid.
It's an acid, exactly right. And based on it, that's based on its name of carbonic acid. So don't be shy to use what we've learned in the chapter on nomenclature to help you with your classifications. So carbonic acid is also a weak acid. It's a pretty interesting weak acid because it's unstable. And as we'll see later on, it's often responsible for the evolution of bubbles or gas seen in some acid-base reactions. Okay, let's look at this next compound. Let's look at this next compound. So what key signpost, what key feature of this molecule stands out to us? C6H5NH2. What does this NH2 or amine functionality tell us? Are we dealing with an acid or a base?
Acid.
So when we looked at our previous discussion of weak bases, the hallmark of a weak base is this amine functional group. So we would then be able to conclude, looking at this formula for C6H5NH2, that we're dealing with a weak base, and we have mainly molecules in solution. So we have primarily C6H5NH2 with a little bit of hydroxide and C6H5NH3 plus. So the amine functional group is a key signpost that you're dealing with a weak base. Does that make sense to everyone? Any questions on that idea? Any questions on that example? Okay, let's look at this next formula. So we have CH3, CH2, OCH3. So does this formula match any of the features of an acid or base?
No.
Yeah, so since it doesn't match any of those features, we just say it's neither. Okay, the last one is a hallmark, pretty classic example of what kind of species. So calcium hydroxide is an example of a strong base, and it dissociates readily in solution. So for strong bases, we have mainly ions in solution. Does this example make sense to everyone? You're going to want to be able to identify your strong acids, strong bases, weak acids, and weak bases, as it's critical for performing calculations effectively and efficiently. Okay, so let's talk about a classic pattern of reactivity observed in acid-base reactions, and that is a neutralization reaction, otherwise known as an acid-base reaction. It's characterized by the transfer of H+, a proton, from an acid to the base. So in this case, we are transferring a proton in the reaction of sodium hydroxide and oxalic acid. As we notice from the formula for oxalic acid can donate 2 protons. So as a result, we need 2 sodium hydroxide molecules to accept those protons. So an acid-base reaction is characterized by the transfer of 1 or more protons from our acid to our base. That in turn generates the conjugate base. I'm going to put this in quotes because it's not in this case, it's not a genuine conjugate base. And the conjugate acid. Okay, so an acid-base reaction is characterized by the transfer of a proton from the acid to the base. Wonderful. So, after this proton transfer process, we end up generating the conjugate base of our starting acid and the conjugate acid of our parent base. So this is the typical acid-base reaction. There are many different possible formulas for your acid and for your base, but they all follow the same general scheme. Does this make sense to everyone so far? Does this make sense to everyone so far? Perfect. So now, let's talk a little bit about conjugate acid-base pairs. So they're commonly written as HA/A-, where you have the acid followed by a slash and then the conjugate base. So for example, H2O/OH-. Now, the conjugate acid-base pairs have very strict definitions. The acid contains 1 more proton than the conjugate base, and it's on the reactant side of the chemical equation. The conjugate base contains exactly 1 less proton than the acid, and it's formed when a proton is removed from the acid. The conjugate base is going to typically be an anionic species, not always, and the conjugate base, by definition, is on the product side of the chemical equation. It's produced. Now, the base contains 1 less proton than the acid and conjugate acid. It's typically an anionic species, and the base is on the reactant side. So the base or the parent base is on the reactant side, while the conjugate base or the base that's produced at the end of the reaction is on the product side. Does that make sense to everyone? Does everyone see that distinction? Base, reactant side. Conjugate base, product side. Likewise, the base, when it reacts, generates the conjugate acid, which contains exactly 1 more proton than our parent base. And the conjugate acid is always on the product side of our chemical equation. Do these definitions make sense to everyone so far? Does everyone feel comfortable identifying the parent acid base, conjugate acid, and conjugate base?
Professor, which one did you say was the parent base?
The base is also known as the parent base. So another word, another sort of classification for the base is called the parent base.
Oh,
Likewise, the acid is often called the parent acid, as it's the species that's engaging in our chemical reaction, while the conjugate acid and base are produced from the reaction.
okay.
Does that make sense?
So the conjugate base is what's produced from the parent base?
It's produced from the parent acid. So think of it like an arrow. The acid reacts to make the conjugate base, while the base reacts to make the conjugate acid.
Okay.
Does that make sense?
Yes, thank you.
Perfect. So now that we have our definitions out of the way, let's look at different types of acid-base reactions. So strong acids can donate H plus to strong bases to form water and a salt. Okay, so would someone like to give us an example of a strong acid? What's an example of a strong acid for us to go with? Would someone like to propose a formula for a strong acid? H2SO4, sure. So a strong acid can react with a strong base, such as lithium. Let's do calcium hydroxide just to make things a little bit interesting. And they react to form water and a salt. And the beautiful thing about this idea is that you can figure out the formula for the salt by crossing your cation and conjugate base anion charges, and that gives us calcium sulfate. We then have to adjust our coefficients, and we see that we need 2 waters. So just to help everyone see what's going on here, sulfuric acid is our acid. It's reacting to make a salt, and this salt contains our conjugate base. Our conjugate base is sulfate. Our base in this case is calcium hydroxide, and calcium hydroxide has reacted to yield our conjugate acid, which is water. Overall, in this process, we have transferred a proton from our acid to our base twice because there are 2 hydroxide equivalents. And conveniently enough, sulfuric acid has 2 protons. That's why we make 2 water molecules. Does that make sense to everyone? Does this idea of strong acid, strong base reactions make sense? Okay, so let's look at an example now of a strong acid reacting with a weak base. What's another example of a strong acid? Does anyone have another formula for a strong acid that we can use?
Hydrochlorine.
Yep.
Hydrochlorine.
Sure, HCl. Yep, that's okay. And a weak base, what's an example of a weak base? Does anyone have an example of a weak base? What's our go-to weak base? Ammonia. I'd like you just to remember the amine functionality. It's a hallmark of weak bases that you'll see commonly in this class. There are others, such as the conjugate base of a strong acid, but ammonia is a pretty nice go-to. So strong acids and weak bases will react to give a weak acid and a conjugate base. So hydrochloric acid is our strong base, and ammonia is, hydrochloric acid is our strong acid, and ammonia is our strong base. Not quite our strong base in this case, it's a weaker base. And the strong acid and weak base are going to react. Hydrochloric acid is going to donate a proton, and in turn, we generate a weak conjugate acid. And this conjugate acid is pretty weak. And when hydrochloric acid reacts, it generates a very weak conjugate base. So when you have a strong acid and a weak base reacting, you make a weak conjugate acid and a very weak conjugate base. So we aren't generating water anymore in this case. Does this example of a strong acid, weak base reaction make sense? Any questions on this example? Okay, so let's keep going now. And let's talk about weak acids reacting with strong bases. So what's an example of a weak acid? What's an example of a weak acid?
Ammonia.
Weak, what was that?
Ammonia.
Is ammonia, so ammonia we established was a weak base. What would be an example of a weak acid? So what's an example of the acid that's not on our list of strong acids? Would anyone like to volunteer a sample formula or name?
Phosphoric acid.
Sure. We can look at phosphoric acid. So phosphoric acid will react with strong bases, and in turn, we'll generate a weak base. So our go-to strong base is a hydroxide salt. So let's go with lithium hydroxide. So at the end of this reaction, we end up generating water and a weak base, which is lithium hydrogen phosphate. So in this case, we have generated a weak base, and this is our conjugate base. Does that make sense to everyone? So these are common patterns of reactivity that you see in acid-base reactions. Now, where things get a little bit interesting is when you have a weak acid and weak base reacting, they undergo a reversible reaction. And we call this process where we have these competing forward and reverse reactions an equilibrium. And this is represented using these back and forth arrows. So for our forward reaction, we have ammonia reacting with hydroxide to yield ammonia and water reacting to yield ammonium and hydroxide. In our reverse reaction, we have ammonium reacting with hydroxide to make ammonia and water. And these two reactions are competing. And eventually their rates reach a steady state. And this process and this steady state is known as an equilibrium. So weak acid and weak bases react reversibly. It's a reversible reaction. And that's important to keep in mind, as that allows us and that informs how we deal with weak acids and weak bases. Any questions on these different types and patterns of acid-base reaction?
Professor, I have a question. When we're choosing the common strong acid, is it just the list that you had given on the previous page?
Yep, exactly right.
And how come the NH3 is not on there, or I don't see it?
Because ammonia is a weak base.
Oh, okay. The list on here are just strong acid.
Yep, exactly right. Exactly right.
Is there a
And
different list that we can look at for weak acids?
no, because it would be huge. There are way more weak acids than strong acids, so it's easier to memorize the strong acids. And then if you find an acid that's not on the list, it's likely going to be weak.
Weak acid. Got
Does
it.
that make sense?
Yes, thank you.
Perfect. So now, when we think about weak acids and weak bases, we discussed this idea of a reversible reaction. So if we put a weak acid or weak base in water, it reacts reversibly with water. And eventually, these forward and reverse reactions reach a steady state or an equilibrium. Now, the main feature of an equilibrium is there is a steady state concentration of each reactant and product. So at this equilibrium, there is a defined concentration of H3O plus, F minus, and HF. And what we're going to talk about next is how to describe this equilibrium and use these equilibrium expressions to talk a little bit more about weak acids and strong acids and start to put some numbers to our descriptions of acid strength and base strength. So let's delve forward with that. So the principal value that we're going to be looking at in this chapter is known as the ionization constant of acids and bases. Now, acids and bases ionize in solution, and this process is reversible and an equilibrium. We can represent the steady state concentration of dissolved ions and molecular species, anything with an aqueous symbol, using an equilibrium constant called the acid ionization constant, Ka. Ka, for a sample equilibrium, Ka is written as product, the concentration of products, over the concentration of reactants, accounting for any coefficients. In this case, they're 1. So in this case, Ka, we're looking at the concentration of our products, which are H3O plus and A minus, over the concentration of our reactants with an aqueous symbol, so Ha. Now, the main thing that I'd like you to note is that Ka is proportional to the concentration of H3O plus in solution. So in turn, the larger our Ka value, the stronger acid we're dealing with. The more H plus we have in solution, the more dissociation and reaction with water to make H plus that we see. So the bigger your Ka value, the stronger your acid. Does that make sense to everyone? Does everyone see that relationship between Ka and acid strength? Strong acids dissociate readily, make a lot of product, make a lot of H3O plus. More H3O plus is on the top, bigger Ka, stronger acid. Does that make sense to everyone? Can I get some feedback in the chat that everyone follows with that? Large Ka, strong acid. Now for bases, we represent the concentration of each dissolved ion using the base ionization constant, Kb. And again, Kb is written in terms of the concentration of product over the concentration of reactant. And as we notice, Kb is proportional to the concentration of hydroxide. So a larger Kb indicates a stronger base. Stronger bases dissociate or react to make hydroxide more readily. Larger Kb, more hydroxide in solution, stronger base. Does that connected idea make sense? Does that related idea make sense? Okay, now we have these equations that are going to serve as our foundation. Now, let's talk about how we can use them for calculations. So first, let's talk about how if we're given the Ka values, how can we use these Ka values to calculate concentration? So remember, Ka is universally defined as the concentration of H3O plus times the concentration of A minus over the concentration of HA. So in this case, we're given the Ka for benzoic acid. So our Ka is 6.3 times 10 to the negative fifth. So what is our concentration of HA? What is our parent acid? What is our parent acid in this expression? What is our parent acid? What is our neutral species? What is our neutral species? What is our neutral non-anionic species? What is our parent acid? If we're looking at the Ka for benzoic acid, so let's write this out. So we have benzoic acid and it's in equilibrium with H3O plus and C6H5 CO2 minus. So what's our parent acid in this problem? What would our parent?
6H5COH.
Well, yes, exactly right. Our parent acid in this case would be benzoic acid. And we know what is the concentration of benzoic acid that we're given in this problem?
6.3 times 10 to the negative 5.
That's our Ka value. Yep, and we have that, and that's important to know. But what's the concentration? Remember when we put something in brackets, we're describing concentration. And what's the concentration of benzoic acid?
0.1 m.
0.1 molar. Perfect. And what is our A minus? What is our conjugate base?
C6H5CO2 minus.
Yep, exactly right. And do we know the concentration of that species? Do we know the concentration of benzoate?
0.05.
0.05 molar. Okay, So now let's plug this in. So we know that Ka is H3O plus times C6H, the concentration of C6H5CO2 minus over the concentration of C6H5CO2H. Now, plugging in our numbers, we see that we know the Ka as well as our parent acid and conjugate base concentration. So we can solve for H3O plus. And we know that the concentration of H3O plus is equal to Ka times C6H5CO2H over the concentration of C6H5CO2 minus. So plugging that in, we know our Ka value is 6.3 times 10 to the negative fifth. Our concentration of our parent acid is 0.1 molar, and the concentration of our conjugate base is 0.05 molar. Punching that into our calculator, we get 1.26 times 10 to the negative fourth molar. Let me punch that in one more time into our calculator. So we take 6.3 times 10 to the negative fifth times 0.1 over 0.05. And that gives us 1.26 times 10 to the negative fourth that we round following sig figs to 1 times 10 to the negative fourth molar. So as we notice, for this weak acid, do we make a very large do we have a very large concentration of H3O plus? Do we make a lot compared to our amount of parent acid? Do we make a lot of H3O plus?
No.
Comparing these two numbers?
No.
Not very much at all. Weak acids do not dissociate substantially. So the concentration of H3O plus will be small. Does that make sense to everyone? Does that idea of using Ka in calculations make sense to everyone so far?
Just scroll up.
Yes. Mhm.
Thank you.
So just as a recap, we wrote out our Ka expression. We identified our acid and conjugate base, and we are given the concentrations in our problem. We then are asked to solve for the concentration of H plus. So we take our equation and we substitute our known values and we solve for our unknown concentration of H3O plus. In turn, that gives us a very small concentration of H3O plus, which matches the pattern of behavior and reactivity that we observe for weak acids. Does that make sense to everyone? So let's try to apply what we've learned to the following example. So in this case, we're given the Kb for ammonia and the concentration of ammonia and ammonium. And in this case, we're asked to calculate the concentration of hydroxide. Given that Kb has the following general, one moment, let me reset OneNote. So given that Kb has the following general expression, I'd like us to try to take this equation, given these values for ammonia, and calculate the concentration of hydroxide. So you've seen an example for Ka, And I'd like you to try now to solve this example for KB. We're given KB, we're given some concentrations. Let's solve and figure out how much hydroxide we have in solution. Let's work on this example for about 3 minutes, and then we'll discuss as a group. And if you have a question, don't be shy to ask. And it's great to see that we're already seeing responses in the chat. Let's try to get a few more responses, and we'll discuss in about another 2 minutes. Let's try to get a few more responses or some questions in the chat, and then we'll discuss. Okay, so let's talk through this example together. What is our acid in this case? What is our acid in this problem? So we have ammonia.
Ammonia.
Yep, so we have ammonia and it's reacting with water. It's reacting with water to yield ammonium and OH minus. So which one of these two species is our acid? What is our acid?
Water.
Okay, water's our acid. Okay, and looking at our products, which of these species is the conjugate acid? Which of these species is the conjugate acid?
NH4 plus.
Yep, so NH4 plus is our conjugate acid. So that's the HA in this KB expression. So the concentration of HA is the concentration of ammonia. And what's the concentration of ammonia in this problem?
0.1 m.
Okay, perfect. And what is our A minus? What is our base in this reaction? What is our
0.5 m.
Yep, ammonia is our base. And we know the concentration of ammonia is 0.5 molar. So then, solving this equation, we also know, given in the problem, the Kb is 1.8 times 10 to the negative fifth molar. So solving for the concentration of hydroxide, we get Kb times the concentration of A minus over the concentration of HA. Punching that into our calculator, we have 1.8 times 10 to the negative fifth molar times 0.5 molar over 0.1 molar. That gives us a concentration of hydroxide of, so we have 1.8 EE negative fifth times 5. That gives us 9 times 10 to the negative fifth molar. Does this example make sense to everyone? Does this example make sense? So as long as you can identify your base, conjugate acid, and your conjugate base, you're all set for these problems. Perfect. So this is a good stopping point for today's lecture. I'd like you to review these notes, and then on our next class session, we're going to focus on applying these ideas of acid-base reactions to calculations involving titrations. And this will be really helpful for some of the questions in the solutions problem sets related to titrations. So is everyone feeling pretty comfortable with the content so far? Is everyone feeling pretty good from where we left off on this problem set? So I'd like you to read this over, familiarize yourself with the strong acids and strong bases, and then we'll talk about integrating acid-base chemistry and stoichiometry next session.